Welcome back to the deep dive. This is the show where we try to boil down these really dense technical standards, get you the key info you actually need. And today, okay, take a deep breath. We're going vertical. Right up the spine of safety engineering, we're diving into NFPA 14.
Ah, yes, the big one, NFPA 14.
Exactly, the gold standard for standpipes, standpipe and hose systems.
Yeah, and this isn't just like academic. This is deep dive into infrastructure that literally saves lives, floor by floor. You look at any major building, a skyscraper, a huge campus. The firefighter's ability to actually fight a fire in there, it hinges entirely on this standard,
Yeah.
NFPA 14.
Right, it dictates everything. Pressure, flow.
Location reliability. The stuff they count on the second they roll up.
So that's our mission today. We're going to really pull apart the 2019 edition, extract that core knowledge. We'll look at, how history shaped it, the critical pressure rules for high rises.
Which are getting pretty complex.
Oh, yeah. And even new stuff like requirements for boatyards, piers. That's pretty interesting.
Definitely a different environment.
Okay, let's start right at the beginning. Why is this even necessary? Standpipes.
Well, think about it. How else do you get water up 50 stories?
Right. You can't just string hoses up the stairs.
Exactly. It's incredibly slow, takes tons of people, tons of resources. Standpipes make vertical firefighting possible, period.
So NFPA 14 is the rule book for that.
It's the authoritative voice.
Yeah.
Yeah. And, the basic definition is simple enough. It's just an arrangement of fixed piping, valves, hose connections, all that stuff.
Components.
Right, components, all designed for one thing, delivering water to put out fires, protect the building, the stuff inside, and, most importantly, the people.
It's the firefighter's express lane for water.
That's a good way to put it.
And it sounds simple, but you mentioned even the words they use matter, like how you refer to the place the hose connects.
Oh, absolutely. Precision in these codes is, well, it's life safety. You can't have ambiguity in an emergency. So the 2019 edition, they made a real effort to standardize terms. They got rid of older words like outlet or hose outlet. They could be a bit vague sometimes. And they replaced them everywhere with hose connection.
Hose connection. Got it.
Specifically means that permanent outlet on the riser pipe, where the valve is, where you attach the fire hose.
Seems like a small change.
It is, maybe, in wording, but in engineering. That clarity prevents mistakes, dangerous mistakes, costly ones too. Now, before we get into the pressures and flows, the real nuts and bolts, it's really vital for you listening to understand how these NFPA standards actually come about.
Right, this isn't like a government law passed down from on high.
Not at all. They're powerful, yes, but they come from a consensus development process.
Consensus meaning who's actually writing these rules? Because they affect, billions in construction costs.
It means hundreds of people. Volunteers, actually. Professionals.
Volunteer.
Yep. Engineers, fire marshals, manufacturers, academics, contractors, insurance folks, all representing different viewpoints, different sectors. They come together, they debate the technical points, they vote.
So it's a collective agreement, basically.
Exactly. That consensus approach is why the standards are generally seen as technically solid and why they get adopted so widely. Even though they aren't federal law per se, they represent sort of the collective wisdom on safety.
But, and this is crucial, NFPA itself isn't like the police, right? They publish the guide, but they don't enforce it.
Absolutely correct. And they're very clear on this.
Right.
Big disclaimers. They state point blank.
Yeah.
They don't independently test or verify the accuracy of everything in the standard.
Okay.
And they don't police or enforce compliance. That responsibility falls squarely on the authority having jurisdiction, the AHJ.
Your local fire marshal, building official.
Exactly. And the design engineer. They have to interpret it, apply it, enforce it. The standard user has to rely on their own professional judgment.
So it's definitely not just a checklist. It's a detailed guide that needs real expertise.
Precisely.
And things change, right? Technology, materials. Sadly, we learn from incidents, too. How does a standard like this keep up?
Yeah, it has to be what we call a living document. It can't be static. So you get new editions every few years. That's the major update cycle. But even between editions, things can change. You might get a TIA, a tentative interim amendment,
TIA,
or errata,
Yeah.
which are corrections to mistakes. So professionals using the code, they have to track these modifications.
Is there an easy way to see what's changed? Like if I pick up the 2019 version, how do I know what's different from, say, 2016.
Yeah, they make it pretty clear right in the text using symbols.
Hmm.
If you're looking at the 2019 standard, you'll see shaded text. That means a revision from the previous edition.
Shaded text. Got
If
it.
you see a little triangle, the Greek letter delta, that usually means something was deleted or revised inside a figure or a table.
Okay.
And the capital N means something's completely new, a new definition, a new section, a whole new requirement.
Ah, so you can trace the changes. That helps understand the why behind them.
Exactly. You don't have to constantly flip back and forth between old and new versions. It flags the evolution right there.
Let's talk history for a second, because this isn't a new problem, fighting fires in tall buildings.
Oh, definitely not. NFPA 14 goes way back. The first report was drafted in, what, 1912?
Over a century ago.
Yeah, responding to the rise of, well, high-rises back then. It went through lots of revisions in the early and mid-20th century, mostly focused on pretty basic stuff.
Like pipe sizes, water tanks.
Pretty much. But as buildings got taller, more complex, those simple prescriptive rules started, well, they started to not be enough.
Things needed to get more analytical.
Right. And a really big shift towards that, a more modern approach, happened in the 1993 edition.
1993, what was the big deal then?
That was a massive overhaul. The NFPA committee realized the standard was just, frankly, confusing. Hard to use, especially if you had different disciplines working together.
Like engineers, architects, fire service.
Exactly. So they totally reorganized it, made it more user-friendly, was the term they used. It created a more logical flow, like designing a system from start to finish.
And what did that reorganization do functionally?
It really pushed the focus towards performance. Guaranteed flow rates, minimum pressures at the hose, where connections should be located based on actual fire data and experience, not just arbitrary rules.
Made it more outcome-based. Makes sense.
Yeah, it shifted from just follow this recipe to prove your system works.
But you mentioned an even bigger shift, like a fundamental change in engineering came later, around 2010.
2010. That was a seismic event for standpipe design. Huge changes.
Okay, well, what happened?
Two major things.
Okay.
First, and this is the big one, they completely deleted the requirements for pipe schedule design.
Whoa, wait. Kill the pipe schedule. That sounds drastic. Explain that for listeners. Pipe schedule meant you could just look up a pipe size on a chart, right?
Pretty much. Based on the number of connections or the building height, a table told you use 6-inch pipe here, assuming it would work.
So why get rid of that? It seems simpler.
Simpler, maybe, but not reliable enough for complex systems. As buildings got bigger, taller, used different materials, the actual friction loss in the pipe became really unpredictable.
Ah, so the table might say 6 inches okay, but depending on the pipe roughness, the fittings, the actual height.
Exactly. You might not get the required pressure at the top, even if the pipe could theoretically carry the volume. Friction loss is the killer.
So the 2010 rule was?
No more guessing. All standpipe systems must now be hydraulically calculated, full stop.
Wow. No exceptions.
No exceptions. You have to do the math. Prove through calculation that your specific design delivers the required pressure and flow at the most challenging points.
That puts a lot more onus, a lot more liability on the design engineer.
It absolutely does. They have to model it accurately.
Uh-huh.
What was the second big change in 2010? That addressed the height issue directly. Before 2010, system pressure was generally capped at 350 psi.
Okay.
But for super tall buildings, that's often not enough pressure to push water all the way to the top zones.
Right, you lose pressure just fighting gravity.
Precisely. So the 2010 edition allowed express mains. Those are the big pipes feeding the upper zones directly to go above 350 psi, as long as the pipe and fittings were rated for that higher pressure.
Got it. So that enabled taller designs. Which brings us to 2019, our main focus. It sounds like 2019 built on that pressure theme.
It did. First off, the general maximum system pressure for almost everything except those special express mains got bumped up from 350 psi to 400 psi, 28 bar.
Another 50 psi, that's a significant jump. Again, allowing for potentially taller or more complex systems.
Definitely gives engineers more flexibility, maybe handles another, 115 feet of elevation just from that pressure increase alone. It enables designs.
Some more pressure capability. What else in 2019? You mentioned technology integration.
Yeah, that was new. The standard added definitions and requirements for things like distance monitoring and automated inspection and testing.
Okay, that sounds like bringing smart building tech into the standpipe world. How does the code handle that? Because fire protection components usually need strict listings, approvals.
Right, and that's a hurdle for new tech. So the code was pretty pragmatic here. It specifically says that these automated inspection, testing, or monitoring devices don't need a formal listing if they aren't actually subjected to system pressure.
Ah, okay. So if it's like A sensor strapped to the outside of a valve reporting open-close status, or a camera looking at a gauge.
Exactly. Stuff that's just monitoring, not holding back 400 psi of water. Forcing those simple electronic bits to meet fire pump pressure ratings would be, well, impractical and maybe kill the technology adoption.
That makes sense. It's a reasonable carve-out, encourages using the tech without impossible hurdles.
Right. Keep the safety focus on the pressure-bearing parts.
Any other key changes in 2019? Practical stuff?
Yeah, a small but helpful one was about signage, specifically the signs at the fire department connection, the FDC. Previously, you often needed signs stating the exact pressure the fire department needed to pump in. The 2019 rules simplified that. Said those pressure-required signs aren't needed if the required inlet pressure is 150 psi or less.
Why the change?
It basically aligns with standard fire department operations. For most low to mid-rise buildings, 150 psi is a pretty standard pumping pressure. So, no need to clutter the FTC with signs stating the obvious in those cases.
Makes sense. Streamlines things. And the last big one from 2019, the really novel edition.
Yes, the entirely new Chapter 13, all about maritime standpipes and hose systems.
Maritime, like on boats.
Not boats themselves, but piers, docks, marinas, boatyards, places where you have water access but unique challenges.
Wow. Okay, that's a big expansion of scope. We definitely need to circle back to that later. Why a boatyard needs different rules than an office tower.
Yeah, corrosion, movement, exposure. That's a whole different ballgame.
All right, so let's say you're designing a building, you know you need a standpipe. First big decision seems to be, who is this system for? Who's expected to actually use it?
Exactly. That defines the class of the system. And the class mainly dictates the size of the hose connection.
So, Class 1, who's that for? Sounds like the serious one.
Class On is the heavy hitter. It's designed strictly for fire department use, or for personnel with extensive fire department level training.
Okay.
It provides 2.5-inch, 65mm connections. That size is needed for the big water flows, the powerful streams you need for major fires, especially in large buildings or commercial spaces.
Got it. Big fire, big hose. Class 1, what about Class 2?
Class 2 is smaller. It provides 1.5-inch, 40mm hose stations. These usually include the hose, nozzle, and rack ready to go.
And who uses those?
Primarily intended for use by trained building personnel. Think like an on-site fire brigade or employees who've had specific training. Or the fire department might use them for initial attack or mop-up because they're quicker to deploy than the big lines.
More maneuverable, less water.
Right. Though the code does allow, in some light hazard places, even a 1-inch hose if it's properly listed and the AHJ approves.
Okay. And Class 3 sounds like a mix.
Exactly. Class 3 is a combination. It provides both. You get the 1.5-inch stations for the trained occupants, and you get the 2.5-inch connections for the fire department.
Best of both worlds. Offers flexibility.
It does. But there's a really important exception, or allowance, I should say.
Yeah.
If the building is fully protected by an approved automatic sprinkler system.
Like NFPA 13 sprinklers everywhere.
Right. Then you're allowed to omit the Class 2, the 1.5-inch hose station.
Oh. So if it's fully sprinklered, you might only see the 2.5-inch connections, even if it's technically Class 3.
Correct. But there's a catch.
Always a catch.
You still need to provide the capability for that smaller hose line. So at each 2.5-inch connection, you have to provide a reducer fitting.
Like an adapter.
Exactly. A 2.5-inch by 1.5-inch reducer, usually with a cap, attached by a chain so it doesn't walk away.
So the fire department or trained staff could still connect a smaller hose if they wanted to. They just need to bring the hose itself.
Precisely. It removes the building owner's burden of maintaining all those hose reels, which can be significant while keeping the option open.
Okay, that makes sense. So those are the classes based on user and connection size. What about how the water gets in the pipe, the operating types?
Right. This is all about readiness and dealing with freezing temperatures. The top tier, the most ready, is the automatic wet system.
Automatic wet. Sounds like what you'd expect.
Yeah. It's permanently connected to a reliable water supply that can meet the system demand. The pipes are full of water, under pressure, all the time.
So you just open the valve, water comes out instantly.
Instantly. That's required for almost all Class 2 and Class 3 systems because they're intended for immediate use by occupants. The only exception is if freezing is a major issue and you have a dedicated, trained fire brigade on site 24/7.
Okay. What if you don't have water in the pipes all the time?
Then you might have a manual system, either manual wet or manual dry.
Manual meaning?
Meaning it has no permanently connected water supply capable of meeting the demand on its own. It relies entirely 100% on the fire department connection, the FDC.
Ah, so the pipes are there, but they're empty, or maybe wet but unpressurized, until the fire engine hooks up and pumps water in.
Exactly. These are generally only allowed in lower-risk, non-high-rise buildings. Though the 2019 standard did specifically add an allowance for manual systems in open parking garages.
Open parking garages, why there?
Well, the thinking is lower fire load, open structure. So they allow manual standpipes in open garages as long as the highest floor isn't more than 150 feet above where the fire trucks can access.
Okay, a practical allowance for a specific building type.
Right. Now, if you need water faster than a manual system, but the pipes might freeze.
That's where the dry systems come in.
Correct. You have automatic dry and semi-automatic dry.
Automatic dry sounds like a dry sprinkler system counterpart.
Very similar concept. The pipes contain pressurized air or nitrogen. Opening a hose valve lets the air out, pressure drops.
And a main valve, the dry pipe valve, opens and lets water rush in.
Exactly. But because there's a delay while the air escapes and water travels, there's a critical time limit.
How fast does it have to be?
If the system holds more than 750 gallons of water capacity,
Which isn't hard in a tall building.
right, then it must deliver water to the most remote hose connection within 3 minutes of opening that valve.
3 minutes. That seems tight, but also maybe long if you're waiting for water in a fire.
It's the maximum acceptable delay. Any longer is considered too risky. Often they need accelerators or quick opening devices to meet that 3-minute mark, especially on large systems.
Okay, so that's automatic dry. What's semi-automatic dry?
Semi-automatic dry also has dry pipes, but water doesn't flow just by opening the hose valve. You have to activate it. There's usually a remote control device like a push button or electric switch located right near the hose connection within 3 feet.
So step 1, open valve. Step 2, hit the button to call for water.
Basically, yes. And these systems also need a separate, independent manual way to activate them as a backup. Plus, those remote activation circuits, they have to be electronically supervised according to NFPA 72, the fire alarm code, to make sure they're working.
More complexity, more supervision needed.
Definitely more complex than just a wet pipe.
All right, let's get into the real engineering meat here. Pressure. This seems like the biggest challenge in tall buildings.
It absolutely is. You've got gravity working against you, pushing water up, which requires high pressure at the bottom. But then you have potentially massive pressure at the lower floors from that tall column of water.
A double-edged sword.
Exactly.
Yeah.
We talked about the system max being 400 psi now in general.
Yeah.
But you can't just deliver 400 psi to a firefighter holding a hose. That's uncontrollable, dangerous.
Right, so you have to knock that pressure down at the connection point.
Precisely. The code sets strict limits on the pressure allowed right at the hose connection itself. And it depends on the hose size.
Okay, break that down. What are the limits for the smaller 1.5-inch connection, the Class 2 type?
For the 1.5-inch 40-millimeter connection used by trained personnel, there are 2 limits. First, the residual pressure, that's the pressure while water is flowing, can't exceed 100 psi, 6.9 bar.
100 psi flowing. Why that number?
It's about nozzle reaction. Keeping the force manageable for someone who might not be a full-time firefighter.
Okay, and the second limit?
The static pressure, this is the pressure just sitting in the pipe before you open the valve, can't exceed 175 psi, 12.1 bar.
Higher static than residual.
Yeah, because the concern there is mostly about the hose itself and the connection handling the pressure before flow starts. 175 psi is generally considered the safe static limit for that size hose and typical building systems.
Got it. 100 flowing, 175 static for the little hose. What about the big one, the 2.5-inch for the fire department?
And for the 2.5-inch 65-millimeter connection, it's simpler but stricter in a way. Both the static and the residual pressure must be limited to 175 psi, 12.1 bar.
175 psi max, whether it's flowing or not.
Correct. Firefighters are trained to handle higher flows, but 175 psi is still considered the practical upper limit for safe and effective handling of that larger hose line in most situations.
So if the system pressure needs to be higher than 175 psi to get water up the building, which it often does,
Then you must install a pressure regulating device, or PRD. A listed PRD. It's mandatory.
the PRD. Okay, this sounds like a critical component. It's taking potentially 400 psi and throttling it down to 175 or 100 psi. What if it fails?
That's the nightmare scenario, right? If a PRD fails open, it could suddenly blast that high-pressure street to the hose connection. Extremely dangerous.
So how does the 2019 code address that risk, especially if one PRD serves multiple connections?
This was a major safety enhancement in 2019. It addresses that single point of failure. The rule is, if you have more than 2 hose connections downstream of a PRD.
Like on a typical floor of a high-rise.
Exactly. Then you need redundancy. The PRDs have to be arranged in series, one after the other.
In series. So the water goes through PRD shack 1, then immediately through PRD shack 2.
Correct. And they have to be set up so that if either one fails completely open, the other one still prevents the pressure from exceeding 175 psi downstream at those hose connections.
Wow. So a built-in backup. If the first one blows, the second one catches it.
That's the idea. It adds complexity, adds cost, but it directly addresses that failure risk.
Serious engineering for safety.
And there's more. The system also needs a bypass line around that series of PRDs.
A bypass? Why?
It has to be an equally sized pipe, normally kept closed with a valve. It allows maintenance on the PRDs, or provides a manual way to get some water to that floor if both PRDs somehow fail closed or get blocked. It prevents total water loss to the zone.
Okay, layers upon layers of control and backup. That really shows the complexity.
It does. It's moved far beyond just simple pipes.
This whole pressure thing naturally leads to the idea of zones, right? You can't just run one pipe system up a super tall building.
No, you definitely can't. A standpipe system zone is just a vertical section of the system. You divide the building vertically.
Why? Just because of the pressure?
Primarily, yes. The pressure limitations of the components, the pipes, the valves, the fittings, the PRDs, dictate the maximum height one zone can serve. You hit 400 psi, maybe less depending on components, you have to start a new zone.
And for those upper zones, the ones sitting way up high, are there special rules?
Yes, redundancy is key again. For every zone above the lowest zone, you need 2 or more separate and direct supply pipes feeding it.
2 pipes going up to the high zone? Why 2?
Redundancy. If one riser pipe is damaged in a fire or fails for some reason, you still have another path to get water up to those critical upper floors. You can't afford to lose the entire water supply high up.
Makes sense. What if the fire department down at street level simply can't pump hard enough to reach those really high zones through the FDC?
Good question. If the building is so tall that fire department sumpers cannot reliably supply the required pressure and flow to the upper zones,
Then what?
then the code mandates an auxiliary water supply for those high zones.
Auxiliary supply meaning? Like a tank on the roof.
That's the most common way. High-level water storage big tanks, often combined with dedicated high-pressure pumps located up high in the building. This ensures the upper zones have their own independent water supply ready to go, regardless of what the fire department can achieve from the street.
So the building itself has to guarantee water for the top floors if it's too tall for the fire trucks.
Essentially, yes. Self-sufficiency becomes mandatory.
Okay, we've talked pressure, zones, backup supplies. Let's talk volume, flow weights. How much water does the system actually need to deliver? This is the core calculation, right?
Absolutely. This is the engine room math, as you called it, and depends primarily on the system class.
So for the main ones, class 1 and class 3, the ones using the big 2.5-inch connections.
The baseline minimum flow rate is 500 gallons per minute, GPM. That's 1,893 liters per minute.
500 GPM. Where does that need to be delivered?
That flow needs to be calculated coming out of the 2 hydraulically most remote 2.5-inch connections simultaneously. So the 2 hardest to reach outlets.
2 connections flowing at the same time. 500 GPM total, or 500 each.
No, 500 GPM total, typically calculated as 250 GPM from each of those 2 remote connections.
Okay. 250 GPM from the 2 toughest spots. Is that always the number?
Not always. There's an important escalator. If you have a horizontal standpipe system.
Like running across a huge single floor plate, a convention center, a massive warehouse.
Exactly. If that horizontal pipe serves 3 or more connections on that one floor, the minimum flow rate jumps up to 750 GPM, 2840 element.
750 GPM. Why so much higher for horizontal runs?
Bigger potential fire area on one level. Need more water available to cover that larger horizontal spread. Calculated as 250 GPM for the 3 most remote connections.
Okay, so 500 GPM minimum usually, 750 GPM for big horizontal layouts. Is there a maximum? You don't just keep adding 250 GPM for every single standpipe in the building, right?
Correct, there's a cap. System design doesn't need to exceed a certain total flow, even in enormous buildings, if the building is fully sprinklered throughout.
NFPA 13 everywhere.
Then the maximum standpipe water supply you need to calculate for is 1,000 GPM.
And if it's not fully sprinklered,
Then the maximum required flow increases to 1,250 GPM.
so sprinklers reduce the total standpipe demand slightly.
Yes, because they provide initial control. The underlying hydraulic calculation still needs to prove you can get 250 GPM simultaneously at the two most remote connections and at the topmost connection of each additional standpipe riser up to that total cap of 1,000 or 1,250 GPM.
Okay, complex calculation ensuring water is distributed. What about the Class 2 systems?
The little hoses.
Much, much lower demand. For Class 2, the minimum flow is only 100 GPM, 379 Elman.
100 GPM.
Where? At the single hydraulically most remote 1.5-inch connection. And importantly, unlike Class 3, you don't need to add more flow for additional connections. 100 GPM total is the requirement.
Designed for first aid firefighting, basically.
Essentially, yes. Limited use. Last question on flow. What if you have a combined system? Sprinklers and standpipes sharing the same riser pipes. How do you figure out the total water needed? You don't want to double count, right?
No, definitely not. The rule is pretty straightforward. You calculate the standpipe demand, like we just discussed, and you calculate the sprinkler system demand, including the hose stream allowance that NFPA 13 requires for sprinklers.
Okay.
Whichever number is greater dictates the required water supply for the combined system.
So you find the worst case scenario, either the standpipe needs more water or the sprinklers plus their hose stream needs more water and design to that higher number.
Exactly. Avoids designing a water supply far larger than necessary by adding the two demands together inappropriately. Okay, so we know the pressure, the flow,
Yeah.
but none of that matters if a firefighter can't actually find or use the hose connection when they need it. Location is critical.
Right. Accessibility starts with basic height, I assume.
Yeah.
Can't be on the floor or way up high.
Correct. Simple rule. The center of the hose valve needs to be between 3 feet, 0.9 meters, and 5 feet, 1.5 meters above the finished floor.
Makes sense. Waist to shoulder height, roughly.
Yeah. And clearance around the valve handle is absolutely non-negotiable.
Clearance. Why?
Think about trying to turn a stiff valve, maybe under pressure, wearing thick firefighter gloves in the dark or smoke. You need room to get leverage. So there must be at least 3 inches, 76.2 millimeters, of clear space between the valve handle and anything next to it, a wall, another pipe, whatever, when the handle is in both its fully open and fully closed positions.
3 inches. That's specific.
It ensures you can get your whole hand around it. Now, if the connection is inside a cabinet, they give you a little break. The clearance requirement drops to 2 inches inside the cabinet.
Okay. Height and clearance. Where inside the building do they have to be?
For Class I systems, the main locations are stairwells. You need a connection at each main floor landing within every required exit stair.
Main floor landing. Not necessarily intermediate landings between floors.
Generally, the main floor landings. And a huge safety point.
Yeah.
The connection must not be located where a door open or closed could block access to it or obstruct its use.
Yeah, you don't want a fire door swinging shut and cutting off your water supply mid-fight.
Absolutely not.
What about horizontal exits, like doorways through major firewalls separating building sections?
Good question. At horizontal exits, you generally need connections on both sides of the firewall, right near the opening.
Both sides. Why?
So crews attacking the fire from either direction or retreating have immediate access to water right at that crucial barrier point.
Makes sense. Is there an exception?
Yes, you can omit the connection on one side if all the floor area on that side is still reachable from the connection on the other side, staying within the allowed travel distance limits.
Ah, the travel distances. Let's talk about those. How far away can the fire be from the nearest hose connection?
This dictates how many connections you need per floor. It depends on sprinklers. In a building without sprinklers, the absolute furthest point on any story must be within 150 feet, 45.7 meters, of a hose connection. That's measuring the actual walking path.
150 feet. That's not super far when you're dragging a heavy charged hose line.
It's not. Now, if the building is fully sprinklered according to NFPA 13 or 13R,
Then you get a bit more distance.
yeah, the travel distance limit increases to 200 feet, 61 meters. The sprinklers provide some initial fire control, buying a bit more hose stretch time.
Okay, 150 unsprinklered, 200 sprinklered.
What about Class 2 systems, the ones with the hose already attached?
Because that hose is typically shorter and lighter, usually 100 feet max, the reach is less. For Class 2, all parts of the floor must be within 130 feet, 39.7 meters of a hose connection.
Tighter spacing for Class 2. Got it. What about roof access? Do you need connections up there?
Yes. If a required exit stair actually goes up and opens onto the roof, you need a connection at the highest landing before the roof door.
And if the stair doesn't go to the roof, then you generally need a single connection installed somewhere on the roof itself.
Unless
the roof is really steep. If the slope is 4 and 12 or greater, it's considered too steep for safe firefighting operations, so a roof connection isn't required.
Okay, covers most situations. Now, the outside connection, the lifeline. The FDC fire department connection.
Critically important. That's how the fire department boosts pressure or supplies the entire system if needed. And the 2019 edition significantly beefed up redundancy requirements for FDCs, especially for large buildings.
More redundancy. How so?
You now need 2 separate FDCs for each zone in 2 specific cases.
2 FDCs per zone. Wow. What are the cases?
First, all high-rise buildings. Second, any building or group of attached buildings where the total outside perimeter distance is more than 900 feet, 274 meters.
900 feet perimeter. That's a huge footprint, like a massive warehouse, mall, or factory complex.
Exactly. For those really big structures, needing 2 FDCs ensures the fire department has connection points on potentially opposite sides, improving access regardless of where the fire is or where they can position their trucks.
Makes operational sense. Where do these FDCs need to be physically located?
Placement rules are strict for speed and visibility. They must be obvious, easily recognizable, located within 50 feet, 15.2 meters of the street, or the closest spot a fire truck can park.
Close to the truck.
And they must be located not more than 100 feet, 30.5 meters, from the nearest fire hydrant that's connected to an approved water main.
Ensures they have a water source nearby to feed the FDC. Got it. How big does the FDC need to be? How many inlets?
That ties back to the system demand we calculated earlier. You need one 2.5-inch inlet for every 250 GPM, 946, of required system flow.
So a 1,000 GPM system needs at least 4 inlets on its FDCS.
Correct. The FDC size directly reflects the system's water needs.
Okay, let's pivot to that new Chapter 13 you mentioned, Maritime standpipes. This sounds completely different. We're not inside a climate-controlled building anymore.
Not at all. Think about a marina, a commercial pier, a boatyard. What are the conditions?
Saltwater, wind, rain, sun. Things move with the tide. Boats bump into stuff.
Exactly. Constant exposure to corrosive environments, extreme weather, physical movement, potential impact damage.
Yeah.
A standard standpipe designed for an office building just wouldn't last or might not work when needed.
So Chapter 13 is specifically for standpipes on marinas, boatyards, marine terminals, piers, docks, wharves, those kinds of places.
Correct. And the design has to explicitly consider all those unique challenges.
So materials must be a big focus. Regular steel pipe would rust away pretty fast.
It certainly would. While the standard still allows typical materials like specific ferrous pipes or copper, if properly protected or rated, it also opens the door for more robust options. It permits listed underground rated pipe beneath piers. And very importantly, it allows specialized materials like listed high-density polyethylene HDPE pipe, if the AHJ approves it.
HDPE, that's like tough plastic pipe.
Very tough. It's highly resistant to corrosion, which is key in salt water, and it's flexible, which helps with the movement aspect.
Okay, HDPE handles corrosion and flexing, but it's plastic. What about fire? Isn't there a risk the standpipe pipe itself could melt or burn through?
That's a huge concern, and the chapter addresses it directly. First, all piping needs protection from mechanical damage getting hit by boats or equipment. For non-metallic pipe like HDPE, if it's on a floating pier, any part that sticks up above the water level usually has to transition back to a corrosion-resistant metal pipe, unless it's a system that's always filled with water.
Ah, so the part exposed to air and potential fire needs to be metal?
Generally, yes. Or the plastic pipe itself must be protected from fire exposure.
How do you protect plastic pipe from fire?
Usually with things like listed fire wrap insulation or by encasing it in concrete. The goal is to ensure the pipe maintains its integrity and keeps delivering water, even if the surrounding dock structure catches fire.
Okay. And the movement. Tides going up and down, docks shifting. How does the piping handle that without breaking?
Design for flexibility is mandatory. You have to use specialized flexible couplings or expansion joints in the piping system. These allow the pipe to move with the tides or accommodate movement between different sections of a floating dock system without putting stress on the pipe joints.
So the whole system has to be able to sort of undulate with the water?
In a way, yes. And the engineers also had to verify that the pier or wharf structure itself can handle the weight of the standpipe system when it's full of water. That's a significant load.
What about the design rules? Like how much water, where do the connections go on a long pier?
It typically defaults to requiring Class I systems, the 2.5-inch connections for high-volume flow. And the spacing is quite tight. You need hose connections located so that no part of the walking surface of the pier or wharf is more than 130 feet, 39.7 meters away from a connection.
130 feet reach. That's the Class 2 distance we talked about earlier, but applied to Class I here.
Right. And to achieve that, Connections usually need to be spaced no more than 150 feet, 45.7 meters apart, along the pier. It ensures rapid access anywhere along the structure.
Makes sense. Fires on piers can spread fast with wind. Draining these systems must be tricky, especially if pipes run underwater.
Yeah, maintenance is a challenge. For piping that runs underwater, the code requires a way to get the water out for service or freeze protection if it's a dry system. Usually this means designing an air blowout connection where you can force compressed air through to push all the water out, unless you provide other drains for low points.
Okay, bloat it out with air. Interesting. What about the FDC? The fire department connection. Could be different responders here.
Could be. You might have fireboats responding in addition to land-based trucks. So the standard says you have to consult with the local AHJ of the fire department to figure out if you need a separate FDC that's specifically accessible by a fireboat.
So boats can hook up directly from the water side?
If deemed necessary for that location, yes. Provides another way to supply water if land access is blocked.
And testing. If you use that flexible HDPE pipe, does the standard pressure test work?
Good point. Standard hydrostatic testing methods might not be appropriate for HDPE's properties. So Chapter 13 requires that if HDPE pipe is used, the pressure testing has to follow a specific different standard, ASTM F2164.
A specific test for plastic pipe.
Right. It's a recognized standard for field leak testing of polyethylene pressure pipe using water pressure. Ensures the test method matches the material, #H8, installation, testing, and documentation, acceptance criteria.
Okay, let's bring it back to more typical buildings, installation and testing. Once the design is done, how do you make sure it's put in right and actually works? Protection of the pipes themselves seems key, especially in high-rises.
Absolutely critical. If the standpipe riser fails because of fire exposure halfway up the building, the whole system above that point is useless.
So how do you protect the pipe?
In high-rise buildings, and even in non-high-rises that are only partially sprinklered, the standpipe piping itself generally needs dedicated fire protection. There are basically 3 ways to do it.
Okay, what are they?
1, enclose the pipe inside a required fire-rated exit stairway. That sterile enclosure protects the pipe.
Simple enough if the pipe runs in the stairs.
2, enclose the pipe in its own separate fire-rated shaft or enclosure. Basically build a rated box around it. The rating has to be at least equal to the rating of the exit stairs.
Also protective, maybe more space-intensive.
And 3, use a listed fire-resistive material applied directly to the pipe itself, like a fire wrap system.
Wrapping the pipe in insulation.
Specialized, listed fire-resistive wrap, yes. It's complex to install correctly, but sometimes it's the only option, especially in retrofits or tight spaces.
And this protection applies to?
Generally applies to the main Class 1 and Class 3 risers. The smaller Class 2 piping, since it's not usually the primary firefighting supply, often doesn't require this level of fire protection.
Got it. Protect the main arteries. Now, for dry systems, you mentioned they need to drain. That means pitching the pipes, right? Sloping them.
Essential. You cannot have water trapped in low spots in a dry system. It'll freeze or cause corrosion. So all horizontal piping in any dry or semi-automatic dry system must be pitched sloped downwards at least 14-inch for every 10 feet of pipe run.
1/4 inch per 10 feet, that's not much, but enough to get water moving.
Right. But if that pipe runs through a refrigerated space like a walk-in freezer,
Then you need more slope.
significantly more.
Yeah.
The minimum pitch increases to 12-inch per 10 feet in refrigerated areas. Need to be absolutely sure water drains quickly before it can freeze solid.
Okay. Pipes are in, protected, pitched. Now you test. What's the main pressure test?
The hydrostatic test, or hydro test, standard procedure for any new pressure piping. All new standpipe systems have to be filled with water and pressurized for 2 hours.
2 hours? That's a long test.
It is. Ensures even slow leaks are found.
Yeah.
And the pressure has to be the greater of 2 values, either 200 psi, 13.8 bar, or 50 psi, above the normal maximum system working pressure, whichever is higher.
So at least 200 psi, possibly much more if it's a high-pressure system. Measured where?
Measured at the lowest point of the system or zone being tested. That's where the pressure will be highest due to elevation.
Okay, hydro test passed. What else? Cleanliness must be important.
Critical. Before you even do the pressure test, you have to flush the system. All the piping needs to be thoroughly flushed with water to get rid of any construction. Crud, dirt, debris, rocks, tools someone left inside. Well, it happens. Especially important for the pipe between the FDC and the first check valve inside the building.
Yeah.
You don't want that junk getting pushed into the system when the fire department hooks up.
Right, could clog nozzles or damage valves. Okay, flushed, pressure tested. Do you have to actually flow water?
Yes, a flow test is generally required to prove the hydraulic calculations were right. You have to actually flow water from the most remote connections simultaneously at the required design flow rate.
So for that 500 GPM system, you flow 250 GPM from each of the two most remote outlets.
Exactly. To confirm the water supply and pumps can actually deliver it, and that friction losses weren't underestimated.
How do you test manual systems that don't have their own pump?
For manual systems, the flow test is done by having the fire department or testing company pump water into the FTC at the required rate and pressure and flowing it out the top. It simulates actual operation.
Okay. And those PRDs, the pressure regulating devices.
Every single PRD installed has to be individually flow tested as well. You have to verify it delivers the correct outlet pressure under both no flow, static, and flowing residual conditions. Make sure they actually regulate like they're supposed to.
Lots of testing. Finally, documentation. What needs to be left behind?
This is crucial for the building owner and the fire department long term. The installing contractor has to provide a permanent sign.
A sign? Where?
A hydraulic design information sign. It has to be located right at the main water supply control valve, or for manual systems, somewhere easily visible and approved near the FTC.
And what's on this magic sign?
It's the system's cheat sheet. It has to clearly state, 1, the location of the two hydraulically most remote hose connections served by that supply.
Okay, it tells the FD where the worst case is.
2, the required design flow rate. Yeah, you can't put 250 GPM each. And the required residual pressure, either 100 PSI or 175 PSI, at those remote connections. 3, the overall system demand total flow and required static pressure measured back at the supply point, like the pump discharge, and also the pressure required at each FDC inlet to achieve that demand.
Wow, that's the whole performance spec right there on a sign, so the fire chief arriving can look at that and know exactly what the system needs.
Exactly. It's non-negotiable information for effective firefighting operations. And beyond the sign, the owner needs to get final as-built drawings, all the test reports, and the manufacturer's manuals for all the components, including repair parts lists.
And keep those records safe.
For the entire life of the system, especially the acceptance test reports.
Okay, wow. We've gone from 1912 pipe schedules to 400 PSI systems, redundant PRDs in series, maritime requirements. NFPA 14 is definitely not a simple document anymore. It's complex, it's evolving.
It really is.
Yeah.
I think the key takeaway for me is that relentless push towards performance-based design and managing higher pressures. Killing the pipe schedule back in 2010 forced everyone to do the calculations, be precise.
Right.
And now with 400 PSI systems, mandatory PRD redundancy, it just highlights how much modern high-rise safety relies on sophisticated, carefully calculated engineered systems, not just brute force plumbing.
Yeah, it feels like a shift from a relatively passive system that firefighters use to a much more active, complex system that has to function perfectly for them. It needs to actively manage these huge forces just to be safe to use.
That's a great way to put it. And that increasing reliance on complex engineering, on technology, it raises a pretty interesting, maybe provocative question for everyone listening.
Okay, let's hear it.
Well, think about it. Standpipe effectiveness used to depend mostly on, strong pipes and the skill of the firefighter operating the hose. Pretty straightforward. But today, as we've discussed, that effectiveness hinges so much more on this complex dance of PRDs working in series, maybe multiple pumps, automated monitoring systems, specialized high-pressure fittings.
All needing to work flawlessly together.
Exactly. So if system resilience, system safety is now so heavily built upon layers of engineering complexity, mechanical devices, even digital monitoring, how does that fundamentally change how we should think about risk in these modern, super tall, complex settings? Does more complexity, even for safety, introduce new kinds of potential failure points we need to consider?
Is the engineered safety net becoming so complex that its own potential failure becomes a primary risk factor?
Yeah.
That is definitely something to chew on. A fascinating point to end on. Thank you for breaking down this incredibly dense standard.
My pleasure. It's critical stuff.
Absolutely. Hopefully for all of you listening, you feel much better informed about what goes into keeping those standpipes ready. Thanks for joining us on the deep dive. We'll see you next time.